Problem number 7, the level of difficulty is medium level. Let's simplify this expression. Let's simplify this algebraic expression. Like us and subscribe, and let's get started. First of all, let's denote our algebraic fraction as a divided by b and rewrite our polynomial a, which is a squared, a cubed minus 2a squared plus 5a plus 26. Now, from the result which follows from Bezout Theorem, we know that any root of our polynomial must divide free member 26. And we can check, it can be plus minus 1. If we insert instead of a plus or minus 1, it will not be equal to 0. But let's check plus minus 2. And if we insert minus 2 instead of a, it will be minus 8 minus 2 times 4 plus, minus 10 plus 26, which is actually 0. That's why minus 2 is one of the root of our equation, of this equation. That's why our polynomial a can be represented as a plus 2, because this is a minus 2. So a plus 2 times some polynomial of degree 2. To find this polynomial, we have to divide our a by a plus 2. Or in other words, let's divide this polynomial by a plus 2 and find this quotient. Let's perform our division. A cubed minus 2a squared plus 5a plus 26, and divide it by a plus 2. We write here a squared. It gives us a cubed plus 2a squared, and we perform subtraction. Here we have a cancellation, and result will be minus 4a squared plus 5a plus 26. Next we write here minus 4a, and we multiply minus 4a by a plus 2. It will give us minus 4a squared minus 8a, and after subtraction it will give us 13a plus 26. And we have to multiply a plus 2 by 13. It will give us 13a plus 26, and after subtraction it will be 0. In other words, if we divide this polynomial by this polynomial of degree 1, we will have this polynomial of degree 2. We can check that discriminant of our of this polynomial will be less than 0. That's why this polynomial of degree 2 doesn't have real roots. And we write a squared minus 4a plus 13, and this polynomial we write do not exist real roots. And so we represented our a as a multiplication of two polynomials of degree 1 and 2. Now let's look at this polynomial b. This is polynomial of degree 3, and root of polynomial a, which was minus 2, doesn't divide 13. So this polynomial cannot be represented as a plus 2 times something, right? That's why only case this polynomial must be obviously divisible by our quotient polynomial. Let's check it. For this, we divide this polynomial b by this quotient polynomial we had in early division, and we will have another polynomial of degree 1. Let's do it, and let's divide our polynomial b, which was a cubed minus 5a squared plus 17a minus 13, divide by polynomial a squared minus 4a plus 13. Here we will have a, which gives us a cubed minus 4a squared plus 13a, and after subtraction we will have minus a squared plus 4a minus 13. Here we have minus 1, and if we multiply minus 1 by this polynomial, we will have minus a squared plus 4a minus 13, and after subtraction we will have 0. That's why this our polynomial, which was in denominator of our problem, can be represented as multiplication of this polynomial and this polynomial. Or in other words, b is equal to a minus 1 times a squared minus 4a plus 13. And let's rewrite our problem. Our problem was a divided by b. So in b, in denominator of our fraction, of our algebraic fraction, we will have this. Let's rewrite it. And numerator of our problem had this. Let's rewrite it. A plus 2 times a squared minus 4a plus 13. After this cancellation, we will have a plus 2 over a minus 1. And this is the final answer of our problem. So our complicated algebraic fraction is equivalent to this simple algebraic fraction. Of course, here we have to claim that a is not equal to 1 because we don't want 0 in denominator of our answer. Thank you very much for your attention. Have a great day.